Okay, let's dive in. We're talking about something truly immense today. Picture the absolute granddaddy of all volcanic eruptions in, well, human history. The Toba super eruption, Sumatra, Indonesia, about 74,000 years ago. This thing was off the charts. A VEI 8, Volcanic Explosivity Index 8. That's basically the biggest known explosive eruption in the last couple of million years, the Quaternary period.
It really is hard to wrap your head around a VEI-8. We're talking over 1,000 cubic kilometers of material blasted out. Just imagine burying a small country under rock and ash, that kind of scale. And Toba is the only one like that we found in recent geological time. It's unique.
Exactly. And that mind-bending scale is what we're digging into today. This deep dive, we're looking at the fallout, the consequences of this monster event. We're pulling from scientific papers, geological clues, archaeological finds, some really surprising stuff. Our mission really is to try and figure out how this eruption might have changed the world, and especially how it hit our early ancestors.
And the timing is just fascinating, isn't it? 74,000 years ago. That's a really pivotal moment in human evolution. Homo sapiens were starting to move out of Africa, meeting other kinds of humans. So Toba lands right in the middle of that unfolding story. Understanding its impact is like looking at a potential major fork in the road for us.
Yeah, and it's a story with some real twists. The initial idea, was that Toba almost wiped humans out, a population bottleneck. But then newer stuff points maybe more towards resilience, adaptation, people actually doing okay in some places.
Exactly. There's evidence that cuts both ways. It's a proper scientific debate.
So we've got sources looking at both sides. It's going to be interesting. Where do we even start with something this huge?
Well, let's ground ourselves in the eruption itself first. Location. Modern-day Lake Toba, Sumatra, Indonesia. That's the spot. Timing. Around 74,000 years ago, you might see 75,000 in some places, but we're in that ballpark.
A slight difference, yeah. That's pretty common with dating things that far back, right?
Oh, absolutely. The science is always getting refined, but we're firmly in the late Pleistocene epoch.
Okay. And the magnitude VEI 8.
Yeah.
Just immense power. What did that actually do? What were the immediate, effects on the ground?
Well, one of the most obvious and widespread effects was the ash. Just unbelievable amounts of ash. The sources say the entire Indian subcontinent got covered in about 5 centimeters. That's what, 2 inches?
2 inches of ash across all of India.
Yep. But it went much, much further than that. We found tephra, that's the volcanic rock fragments, the glass way out in the South China Sea.
Yeah.
Even in deep sea mud, abyssal sediments in the central Indian basin.
Oh, wow.
It tells you just how far this stuff traveled. Truly global reach.
Just imagine that. The sky goes dark, this gritty stuff starts falling for potentially weeks, covering everything for thousands of miles. And the place where this happened, the volcano itself, that's Lake Toba now, right? The lake is the result.
Precisely. Lake Toba sits in the caldera. That's the huge depression left behind when the volcano blew its top and the ground collapsed into the emptied magma chamber. It's a pretty dramatic geological monument to what happened there.
Okay, so huge eruption, ash everywhere. This leads us straight to the volcanic winter idea. The theory that this event basically triggered a global deep freeze. That was the big theory for a while, wasn't it?
Oh, definitely. Back in 1998, Stanley Ambrose, an anthropologist, put forward this idea. The thinking was, all that sulfur dioxide shot into the stratosphere turns into sulfate aerosols. These tiny particles act like little mirrors, reflecting sunlight back to space.
Causing cooling.
Right. And the initial estimates were pretty drastic cooling. Some suggested maybe even 15 degrees Celsius globally.
15 degrees, that's catastrophic.
That was the idea. Widespread ecological chaos, crops failing, potentially pushing human populations towards extinction.
Plus, you'd expect less rain, big shifts in where plants could grow.
Yeah.
A really grim scenario.
A very bleak picture, yeah. But the science has moved on a bit, hasn't it? Our sources point to challenges to that original theory. What's the counter evidence looking like? Well, several things have emerged that make that extreme scenario look less likely. For one, researchers looked at sediment cores from Lake Malawi in East Africa, crucial area for early humans, and they found no signal, no evidence of a sudden, really catastrophic cooling event right after Toba.
So in at least one key spot, the impact wasn't that bad.
It suggests it might not have been as uniform or as severe as first thought, at least not everywhere. And also our climate models have gotten way better. Newer simulations with more sophisticated understanding of how those aerosols work in the stratosphere. They now suggest the peak global cooling was probably more like 3.5 degrees Celsius.
Okay, 3.5 is still significant, but it's a lot less than 15.
Exactly. A big difference. And crucially, these models also suggest the effect was shorter lived. those sulfate aerosols, they probably washed out of the stratosphere, returning things to near normal within maybe 4 or 5 years.
So not a decades-long super winter.
Right, that idea, the Toba catastrophe theory causing near extinction. Many scientists now think that's, well, largely debunked.
Okay, that changes the picture quite a bit. So if the deep freeze wasn't the main story, what does the archaeology tell us? How did people actually cope?
This is where it gets really interesting. We have some amazing evidence, especially from South Africa, at sites like Pinnacle Point and another called Vleesbaai. Archaeologists found cryptotephra.
Cryptotephra. Micro what now?
Yeah. Microscopic shards of volcanic glass. Tiny, tiny fragments. But their chemical signature is like a fingerprint, and it perfectly matches the Toba eruption.
Wow. So tiny clues linking these sites directly back to that massive event thousands of miles away.
Precisely. And they found these shards within archaeological layers.
Layers showing people were living there.
Yes, and this is the key bit. The layers show continuous human occupation. People were there before the ash layer, during the time it was deposited, and right after. No break.
So no wipeout, at least not there.
Exactly. It directly challenges that near-extinction idea for those populations. In fact, some evidence suggests that people in South Africa actually kind of thrived after the eruption.
Thrived? What does that look like in the archaeological record?
Well, researchers noticed that soon after that Toba ash layer appears, there's a shift in the stone tools people were making. They become more complex, new innovations appear.
Like they got smarter with their tech?
It sort of, yeah. New techniques, maybe more efficient tools. And these weren't just temporary tweaks. These innovations stuck around for thousands of years. It suggests a period of, cultural advancement, technological problem solving.
That's incredible. Facing a major environmental event, and instead of collapsing, they innovate. It wasn't just survival, it was progress. And this isn't just a South African story, is it? You mentioned Ethiopia, too.
Right, the Shinfa-Masemo-1 site in Ethiopia. Another fascinating piece of the puzzle. The geology there suggests the climate did get drier after Toba, more arid.
Okay, so some climate impact there.
Yes.
Yeah.
But again, the humans didn't just disappear, they adapted. Analysis of the animal bones and plant remains found at the site shows a big shift in their diet.
What did they switch to?
Fish. A lot more fish.
Fish. So the landscape gets drier and they start fishing more. How does that work?
Well, think about it. If it gets drier, rivers might shrink. Lakes might break up into smaller pools, right?
Okay, yeah. Water holes.
Exactly. And those water holes become natural traps for fish. Suddenly, fish are easier to catch, concentrated in these spots. It becomes a reliable food source in a tougher environment.
Clever. Adapting the menu to fit the conditions.
Precisely. It shows what researchers call the plasticity of Homo sapiens. Our incredible ability to figure things out, to adjust to wildly different conditions.
That adaptability is key. And this fishing adaptation leads to another interesting idea, doesn't it? These blue corridors.
Yes, exactly. If fish became more readily available in these concentrated water sources during dry periods, these spots, these fish-rich waterholes along river systems, might have acted like corridors, pathways.
Pathways for migration.
Potentially, yes. Facilitating human movement, maybe even out of Africa. It's an alternative idea to the more traditional green corridor theory.
Which is about people moving during wetter periods with more vegetation.
Right. The Ethiopian evidence suggests that even drier periods might have had opportunities, like these fish resources, that supported human dispersal.
So ironically, this massive eruption, by maybe making things drier in some places, could have indirectly opened up new migration routes based on water resources. That's counterintuitive, but fascinating. Now, going back to that cryptotephra you mentioned, those tiny glass shards, you said they were like a fingerprint. How else do they help archaeologists, particularly with dating?
This is a huge advantage. Dating things from 74,000 years ago is tricky. Standard methods often have uncertainties, error margins, maybe up to 10%.
Right.
That can mean thousands of years of wiggle room.
Which makes it hard to link events precisely.
Exactly. But the Toba ash fall, that was geologically instantaneous. The ash likely settled over vast areas within, say, a couple of weeks, maybe even less. And we've been able to date that ash layer itself very precisely using radiometric techniques. So it's like a time marker, a very sharp one.
Like a pin dropped on the timeline across huge distances.
Precisely. So when we find those Toba shards at Pinnacle Point and also at Vleesbaai, hundreds of miles apart, it lets us sync up the archaeological sequences at those sites. We know what was happening in both places at almost exactly the same moment, relative to the eruption.
That allows for much more detailed comparisons of human behavior across different regions at that specific time.
Absolutely. It provides an incredibly valuable chronological anchor, much better precision than we usually get for this period.
Okay, that's a really powerful tool. Now, we've talked about the revised view of the climate impact, maybe less severe cooling, shorter duration, but our sources bring up another potential stressor from Toba. Ozone depletion. What's the theory there?
Yeah, this is another angle that researchers are looking at. It focuses less on temperature and more on UV radiation. The idea is that all that sulfur dioxide and sulfate aerosols shot way up into the stratosphere didn't just block sunlight, they also interfered with ozone chemistry.
Ozone, our sunscreen layer.
Exactly. The aerosols would have absorbed UV radiation that's needed to actually create ozone up there, so less ozone gets produced.
And a thinner ozone layer means more harmful UV radiation gets through to the surface.
That's the concern. Models looking into this suggest Toba could have caused a pretty significant global ozone drop, maybe peaking around 20% depletion within 6 months or so.
20% globally.
But, and this is important, the effect would likely have been much worse in the tropics, near the equator. Some models suggest the ozone column there could have been reduced by more than half.
50%. Wow. What does that mean for life on the ground in the tropics?
It means potentially very dangerous levels of UV radiation. The UV index could have shot up dramatically. We're talking extreme levels, causing rapid sunburn, serious skin damage, a major hazard for any organisms living there, including humans.
So maybe the cold wasn't the biggest immediate threat everywhere, but this UV radiation surge could have been a major problem, especially near the equator.
It's a plausible stressor, yes. There's a bit of complexity, though. Right after the eruption, the thick volcanic plume itself would have blocked a lot of UV, kind of a temporary shield.
Okay, initial protection.
But as the SO2 converted to sulfate aerosols over months, those aerosols are less effective at blocking UV. So you might get this period after the initial plume clears where the ozone is still depleted, but the aerosols aren't blocking as much UV, leading to that surge at the surface.
Delayed punch from the UV.
Potentially. So the theory is maybe it's this combination. Limited cooling, maybe some regional drying, but severe UV damage in the tropics, plus maybe volcanic winter effects elsewhere. Maybe that combination contributed to population stress.
Okay, so it adds another layer of potential environmental hardship beyond just temperature change. Could this have contributed to that genetic bottleneck idea we mentioned earlier? Did Toba cause a bottleneck?
Well, the idea of a human genetic bottleneck, around this time, it's been around. Some early genetic studies pointed to a sharp drop in diversity, especially outside Africa. But the thinking on this has really evolved. The main explanation now, widely accepted, is the founder effect.
Founder effect. That's about small groups leaving a larger population, right?
Exactly. Imagine you have a big population with lots of genetic variety. If only a small group leaves to colonize a new area, they only take a small sample of that original genetic diversity with them.
So their descendants will naturally have less diversity than the original population back home.
Precisely. And that's seen as the primary driver for the lower genetic diversity found in non-African populations compared to African ones. It reflects those initial migrations out of Africa by relatively small groups.
So less about a catastrophe wiping people out and more about the process of migration itself.
Yes. While some early studies tried to time this bottleneck specifically to Toba, more recent, larger genomic studies show a wider range of possible dates. It seems more likely that the bottleneck relates to the dynamics of those early human dispersals, rather than being directly caused by Toba slamming the population down. There was a bottleneck within Africa too, actually slightly earlier and milder, but its cause is still debated.
So Toba might have added pressure, but probably wasn't the main cause of any long-term bottleneck affecting our species' overall genetic makeup. Migration seems key.
That appears to be the consensus now, yes.
Okay, so the story is definitely more nuanced than just volcano explodes, humans almost die out. Now, let's fast forward. Lake Toba today. It's not just a geological feature, it's a place where people live, a whole ecosystem. Tell us a bit about that.
Absolutely. Lake Toba today is this vast, beautiful caldera lake. It's huge. And it's the traditional homeland of the Batak people. They have a really distinct culture, famous for their traditional houses.
Oh, with the big swooping roofs.
Exactly. Those intricately decorated roofs that look a bit like horns or boat hulls. Really striking architecture. And there's a main town, Parapat, On the Edge, which is the gateway for visiting the lake, and Samosir Island.
Samosir Island, that's the big island in the middle of the lake, isn't it? Formed by resurgence after the eruption.
That's right. It's a large island formed by uplift within the caldera.
And the lake itself, it must have its own ecosystem.
It does, though it's what we call oligotrophic, low in nutrients. So that limits the amount of plant life, phytoplankton, at the base of the food web, which in turn means it doesn't naturally support huge fish populations, although there are various zooplankton and bottom-dwelling creatures. There are a couple of native fish species that are almost unique to the lake, like Rasbora tabana, and another called Nulisicillus thenamani.
That's the batak fish.
Yes, the batak fish. Sadly, it's endangered now. Deforestation, pollution, changes to the lake, introduction of other fish.
Ah, like tilapia and carp. You mentioned those were introduced.
Several non-native species have been introduced, which impacts the native ones. It's a common story in lakes worldwide, unfortunately.
A reminder that the impacts continue, both geological and human. And isn't there a folk story about how the lake formed?
Oh yes, a very popular one, the origin of Lake Toba. It involves a fisherman who catches a magical golden fish, who turns into a beautiful woman. Promises are made and broken, and Samosir Island is said to be the son of this magical fish woman. It's a lovely story connecting the people to the landscape's formation.
That's fantastic. It shows how these immense natural features become part of cultural identity. Okay, so let's try and pull this all together. The Toba super eruption. Undeniably one of the biggest volcanic events in recent Earth history. Global reach. Monumental. But its impact on our ancestors, maybe not the simple extinction level event initially proposed, more complex.
That really seems to be the picture emerging, yes. That original volcanic winter causing near extinction. The evidence has largely moved away from that extreme scenario. But that doesn't mean it wasn't tough. There were likely significant environmental stresses, regional climate shifts, maybe that severe UV radiation issue in the tropics. But what stands out more and more from the archaeology from places like South Africa and Ethiopia is human resilience, adaptability.
People figuring things out, changing diets, innovating tools, maybe even finding new pathways across landscapes.
Exactly. It paints a picture of early Homo sapiens as remarkably flexible and resourceful.
And it really highlights how crucial it is to bring different fields together, doesn't it? You need the geologists, the archaeologists, the climate modelers, the geneticists, all talking to each other to piece together this kind of story.
Couldn't agree more. It's that interdisciplinary approach that lets us build a richer, more accurate picture of these deep past events and how they intersected with our own history. And it's a story that's still being written, you know? New discoveries, better techniques, and our understanding keeps evolving.
So maybe the final thought for you listening is this. Think about how these massive, seemingly purely destructive natural events can also be catalysts. Catalysts for change, for adaptation, for innovation. Toba was immense, devastating in many ways, but it didn't end the human story. Instead, the evidence increasingly suggests our ancestors met the challenge. It makes you reflect on resilience, doesn't it? Resilience in the face of planet-scale change. We definitely encourage you to keep exploring this. There's so much ongoing research into Toba's legacy. It's a fascinating window into our deep past.